Hey everyone, welcome back to my Calculus 1 series. In today's lesson we'll be going over the chain rule. So the chain rule deals with when we have a function that is a composition of two functions. So I've written a little definition here and we'll kind of break it down together, but let me just start off by reading it. So if g is differentiable at x and f is differentiable at g of x, then the composite function f, this capital F, is equal to the composition of f of g of x, written like this, f is equal to f of g of x, is also differentiable at x. So we could see why this definition kind of makes sense. We first need to check that g is differentiable at x because it's this inner function right here. And also we want to check that f is differentiable at g of x, not just at x, because we don't really care for x, but we want to check that f is differentiable at this entire function right here, the whole thing, because the function f is going to receive the output of what g of x gave us. So we want to make sure that g is differentiable at its parameter, which is x, and then we also want to make sure that f is differentiable at its parameter, which is this entire function of g of x. So if all of this is true, there's a simple formula we kind of use to break down the derivative of a composite function. So we can write this by saying f prime of x is equal to f prime at g of x times g prime of x. So what we do is first we take the derivative of this outer function and leave the inner function alone. We don't really touch it, as you can see here. And then we multiply by the derivative of this inner function. So we can also write it using Leibniz notation. This is the one that I kind of prefer. We could say that dy over dx is equal to dy over du, and then we're going to multiply this by du over dx. And again, these aren't division signs, but we can kind of envision that we've constructed like a sort of proper statement, because we could see that du is here and then du is kind of at the top. So if we think about it, we can't really cross them out, but it kind of just, to me, that's like a little trick I use to see that I've constructed like a proper chain rule, because I kind of just mentally cross them out and I can see that I'm going to be left with dy and dx, which is the same thing on the left side right here. So that's basically it for the definition. Now we're going to look at some ways as to how we can apply this to some functions. We'll start off pretty easy and then we'll kind of get a little crazy with them. So I'm going to write down a few examples here and we'll go through them. So here's our first example, and we can see that f of x equals the sine of x squared. Now it's really important to identify what the two functions that we're going to be dealing with are. So in this case we have this outer function of sine x and this inner function of x squared. So it's pretty obvious. If we are going to follow the formula, first we're going to take the derivative of the outer function, which is right here, and then we're going to take the derivative of the inner function, which is right here. So first, let's start off by taking the derivative of the outer function, right? We can think of this as like sine of u, where u is equal to x squared. We can kind of do this mental substitution if it helps. So we know that the derivative of this sine of a variable, in this case x squared, but we abbreviated it to u. So the derivative of just sine of u is equal to cosine, and u in this case was x squared, so we can kind of just plug that back in. But we also, like, that substitution is kind of more mentally, like we don't really need to think of it, because we know that first what we do is we take the derivative of the outer function and leave the inner function alone. We kind of just leave it where it is, and then we later on get back to it and multiply it by the derivative of the inner function. So now, as you can see here, we've taken the derivative of the outer function, the sine, and now let's take the derivative of the inner function. So we know that the derivative of the inner function of 2x is just going to be, of x squared is just going to be 2x, because we're going to drop the power and subtract 1. And there you go. We have utilized the chain rule to solve for this derivative of a composition of two functions. So now this next example is kind of going to portray why we need to be very careful when identifying what two functions we're dealing with. So here I've got something that looks like the first example, but it's not quite it. So now we have sine squared of x, and we can rewrite this like this as well. So now the entire sine is getting squared, not just the x. So we can identify kind of the outer function as being u squared, where u is sine x, because this squared operator is getting assigned to this whole thing. And then we can say that the inner function is sine x in this case. So let's go ahead and let's apply the chain rule. So the derivative of this function right here would equal to the derivative of the outer function. And the outer function that we established was this x squared. So the derivative of, let's just think of it as this single unit right here. The derivative of this would just be 2u, but u in this case is going to be sine x. So we can just replace it like that. And again, this substitution, we don't really have to do it. My suggestion is you don't do it, because when you get into the more complex functions, it's almost like too much. So I think it's better to just find out what the outer function is, differentiate it first, and leave the inner function alone. So now that we've done the outer function, we've differentiated it, we're still left to multiply by the derivative of the inner function, which is this sine x. And we know the derivative of sine x is equal to cos x. So now we are finished. We have fully applied the chain rule, and there is no more functions to differentiate. So we finally have our derivative. And you could see how these two functions, they look kind of similar, but their derivatives are completely different. So that's why I wanted to emphasize the importance of finding out what your outer function is and what your inner function is. We want to find out which one composes which. So now let's take a look at a little bit more complex function right here. This is f of x is equal to e to the sine x. So we haven't seen this before, but the process stays the same. For us to find the derivative of this function right here, all we have to do is apply the chain rule. And again, this is a composition of two functions. We could see that this is a composition of e to the x and sine x, where e to the x is the outer function and sine x is kind of that inner function. Now, what we're going to do is first we're going to take the derivative of the outer function, which is e to the x. So the derivative of e to the x is just e to the x, but this x is not just x, it's a sine x there. And again, we don't touch it for the first derivative. So we leave e to the sine x there, and we're going to multiply by the derivative of the inner function, which is sine x. And we know that that derivative is going to equal to cos x. So there you go, we have fully differentiated this function. There's no more functions to differentiate, and that is the derivative. So now let's take a look at a similar function to what we were dealing with before. However, I've added this extra inner function right here of 3x. So now we have a composition of three functions. We basically have something looking like f of g of h of x, right? Where the outermost function f would equal to e to the x in this case. G would equal to the secant of, let's say, x in this case, and then h would equal to, h would equal to 3 to the x. So we can see how these three functions are composed now, and we're going to have to apply a few chain rules, not just a singular one. But the process remains the same. We always want to take the outer function first, take the derivative of it, and multiply by the derivative of the inner function. So first, let's take the derivative of this outermost function, which is f, and it's e to the x. And we know that the derivative of e to the x, we can treat this as a whole unit right now. We know that the derivative of that function is just going to be the same. So it's e to the secant of 3x. And now we want to multiply by the inner function, right? And the inner function is going to be secant of 3x. It's a composition. It's g of h of x. So it's both of these functions here. But we know that the derivative of a composition of functions needs to be a chain rule. So now we need to apply a second chain rule, right? First we had a composition of, like, let's say h of x, where x was g of h of x, right? Because this parameter that f was taking was all of this. But now we need to take the derivative of this, and this in itself, g in itself, has a parameter of another function. So we need to apply a secondary chain rule. So let's only look at secant of 3x, right? The outer function here is secant, and the inner function here is the 3x. So like we do in chain rule, let's take the derivative of secant first. So the derivative of secant is just secant of the value that you have inside, which in this case is 3x, times the tangent of the same x value, which is 3, right? But now we have this inner function to deal with, which is 3x, and we still need to take the derivative of that. So now we need to multiply by the derivative of 3x, which is just 3. And now, as you can see, we're done. We've done the chain rule 3 times because we have 3 composition of functions. So we have f composed of g, which is composed of h. So you could see how that maps to 3 multiplications here. And this is why I don't really suggest breaking the function down like I do here, because it does get pretty messy. I suggest you just identify the function, deal with the outermost function at all times while keeping the inner function constant, and then when you get to the derivative of the inner function, you just kind of piece it one by one, like we did in this problem. So now for the last example, again, I've chosen a composition of 3 trigonometric functions. We have our outermost function, which is sine. We have our secondary outer function, which is cosine. And then lastly, we have this inner function of tan x. Obviously, we could argue that even x itself is a 4th function, but we know the derivative of it's just going to be 1, so I say there's only 3 here. So if we're asked to compute the derivative of this function, we're going to go about it using the chain rule because it is a composition of functions. Again, all we do is we first take the derivative of the outermost function. So the derivative of sine is cosine, and we're going to think of its parameter as 1 unit. So we're just going to copy it. And now we want to multiply by the derivative of this unit. But if we look at this unit, like all of this right here, it in itself is a composition of functions too. So we need to apply the chain rule again. Now we look at this unit and we determine what is the outermost function of this unit. Well, it's cosine. So what is the derivative of cosine? The derivative of cosine is minus sine. And we know that in the chain rule, once we take the derivative of the outer function, we're going to keep the inner function. And the inner function is this one right here, the tan x. So we're going to keep tan x. Now that we've taken the derivative of cosine, we need to take the derivative of whatever it was composed with. So the inside function is now tan x. And we know that the derivative of tan x is secant squared x. Now, like I said, we can argue that x itself is a function, and we still have one more step to go, but its derivative is 1, so I really don't consider it, but maybe you do, so here it is. This is the entire derivative of this function, and we could see that we've done it properly because it maps out to the amount of terms that we have, right? We have this outer function, which is 1, we have this second outer function, which is 2, then we have this inner function, which is 3, and we've included this x as 4, so as you can see, we have 4 terms right here. So that's it for this really quick lesson on chain rule. My suggestion with it is don't get too freaked out when you see these composition of functions. Just deal with the outer function, taking the inner function at the moment as a single unit, and then slowly unravel it by finding the derivative of the outermost function and then the outermost function again, and so on and so forth, applying the chain rule as many times as you need. So if this video has helped you out with anything, please leave a like and comment as to what it helped you with. Like usual, if you're new to the channel, please like, comment, and subscribe. It's greatly appreciated. And yeah, I will catch you guys in another video.